I don't know, when did I get disconnected? When did I get disconnected, people? For how long have I been disconnected? Guys,
Sir,
are you
it
there?
said the meeting, the host has ended the meeting.
Oh, why did they enter the meeting? That's why I think I was kicked out. I think
so we all
have
were out.
Yeah, I'm audible, that I know, but again I have to be made host, I guess. Oh, again I'm the host. Still I'm the host. Okay, cool. No problem. Let me share my screen. Okay, so what I was telling is, wherever I have the least, I will say the maximum efficient back bonding, there I'm going to have least Lewis acidic character. Is it not? Right. Now, how do I decide where do I have more efficient back bonding? Again, we have to go back to the concept of orbitals. A bond. Normally, in general, a covalent bond is formed by overlap of orbitals. Isn't it? I have, for example, a sigma bond is formed when I have head-on overlap. Pi bond is formed when I have lateral overlap. Right? So eventually, at the end of the day, all you have to look into is a better overlap. Right? A more efficient overlap, a stronger bond, more back bonding, lesser Lewis acidic character. I hope you are able to connect the dots. Okay, now we'll just try to see what kind of orbitals are involved in bonding, especially in the back bonding. We're talking only about the back bond. Okay, now you see that boron has an empty 2p orbital. Okay, boron. Okay, let me draw it like this.
Sir?
Yeah.
I've been marked absent.
No problem. You can just text Akila ma'am or Bhaskar sir. They'll change it. Don't worry.
Okay, sir. Thank you.
Okay, right. Fine. So if I have boron that is having an empty p orbital, I'm talking only about the back bonding. Okay. Now this fluorine, in one of the p orbitals, it is having a lone pair. Okay. Now what do you think? They both will laterally overlap to form. Maybe if I can use some other color for boron. This is empty, and the fluorine which is coming is going to have something like this, and here I'm going to have to a coordinate bond. This was empty, right? This was the blue color. Okay, this was the blue color empty. Now it was donated. Now you see that it is having a back bonding in the form of a coordinate bond. Done. So now it will become like this. B, maybe a red color single bond, F, and the blue color double bond, coordinate bond like this. Other two fluorines are there. Don't worry about it. Okay. So I'm talking about this overlap. Okay. Now you're seeing that there is an overlap here. More efficient overlap, more efficient back bonding, less would be the Lewis acidic character. Okay. The same thing happens with the chlorine also, bromine also. Okay, now in all the cases, B is having, that is boron is having only 2p orbital. That is not changing. Only the side atoms are changing, right? Fluorine, chlorine, and bromine, right? So I know in this case, the lone pair is coming from 2p orbital. This is nothing but 2p. For fluorine, it is 2p, right? And I know this lone pair is coming from 3p, and this lone pair is coming from 4p, valence shell, right? Now, can you tell me if I have 2p, 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 3p, and 2p, 4p, which among them is the strongest overlap or more efficient overlap?
So 2p, 2p.
Yes, I told you, the lesser the energy difference, the orbitals which have to involve in the overlap should have same energy. More and more similar energy they have, stronger attraction they are, better overlap they can have, right? So 2p 2p overlap is a stronger overlap than 2p 2p, sorry, 2p 3p, and 2p 3p overlap is a stronger overlap than 2p 4p overlap. Okay, so can I say that strongest back bonding will happen in case of BF because it is 2p 2p, and the least back bond or least efficient back bond for BBR bond. This is the strongest back bonding BB. This is weakest or least back bonding for BR, and BCl is intermediate. Right. So now, if I ask you the acidic strength, the strongest back bonding is happening in the case of BF3. This would be the weakest Lewis acid. Right, and weakest back bonding is happening in the case of BBR, so that would be the strongest Lewis acid. Right, so if I have to arrange them in the order of Lewis acidic strength, BBR3 will be a more of a Lewis acid than BCl3, and the least acidic would be BF3. I hope everybody gets this point. It's all about which orbitals are involved in the overlap. Right. Okay, now this we understood, right? Now you see that I have a lone pair, and that is related to the empty orbital of the next atom. This is exactly going to happen. This is exactly what is going to happen in the case of your resonance also, but it is going to happen more than once. More than once. I can show you resonance here itself. Okay, now we will take the example of BF3. Anybody has any questions now? Please ask me now itself. Any questions till now? Back bonding, how, where, everything, everything is okay. If there's anything, please ask me. Okay, fine. Now, let me take the case of BF3 itself. No. Okay, now let me represent the, this thing with another color. Okay, and I'll represent the lone pairs also with red color. Okay, now I already have a coordinate bond, back bond is present. Obviously, this will have a positive charge because it is donated electron. Okay, right. Now, if I want, this is one time happening. This already, you know how to represent it. I had a lone pair. You put an arrow mark like this. This will come like this as a coordinate bond. Okay, now what can happen is, you see that this lone pair can also be a competitor. Okay, so what can happen is, if this lone pair comes here and make a bond, what will happen? I obviously cannot, I cannot have more than 8 electrons in boron. Not possible. Already I have 8 electrons. 1, 2, 3 normal sigma bonds, 1 back bond, 8 electrons gone. Okay, now if this electron has to involve in this, definitely this bond has to break. Okay, look at how all about homolytic and heterolytic cleavage. Full arrow mark towards this atom, so it will take up the electron. Now this one lone pair coming here, donating electron in the form of a coordinate bond. I can represent it like this. Look at this: B, F, 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 normal. Right now, what happened? This one became your double bond, and this bond was broken. So positive and negative neutralized. Now I would have had 3 lone pairs on this, and only 2 lone pairs on this, and 3 lone pairs on this. Okay, now again this can happen, right? This can come and this can break again. Again, I can rewrite this. B, no. B,
Sir, should
F,
the
what?
sir, should the bond be represented with the arrow only, like when it is breaking and forming?
Yeah, whenever you want to break a bond or whenever you want to make a bond or break a bond, you have to show it only the arrow marks.
Okay, sir.
Okay, now from the lone pair, if you show the arrow towards the already an existing bond, you're going to break a bond. And if you do the ulta, you're from the bond towards one atom, that means you're breaking it. Okay, now see, this is breaking. One bond towards one atom. Again, see, this is breaking. Bond towards one atom. But you see, making of bonds. Lone pair towards the bond. Making a bond. Okay, anyways, you'll get the hang of
Yes,
it. Don't
sir.
worry. Okay, right. So now I will take the red color pen and I saw that there's a double bond now because it's coming. Now this will have only 2 unpaired electrons. The rest, obviously the bond is broken now, right? Or if I forgot to mention a positive charge on this fluorine because it's donating. Okay, so now I would have had 3 unpaired electrons, 3 unpaired electrons, and 3 unpaired electrons. Okay, one time happening back bonding, but this entire phenomena, whatever you are seeing here, this is, my friend, resonance. I told you, movement of pi electrons, right? Delocalization of pi electrons. We'll just go back to the definition. Look at this. Delocalization of pi electrons. What are pi electrons? Electrons in the form of a pi bond. Yes, right? We have a coordinate bond, which is a double bond, which is involving it. That is only moving, right? Okay, that is only moving. And then you see that another thing can be a lone pair, right? You obviously where is it starting from? It is starting from the fluorine, this lone pair, this fluorine, this lone pair, isn't it? Right? So you see that the negative charge can also happen. That we'll see in some other example. Okay, right. Now you see that this is happening, right? The pi electron, this particular pi electron is keeping on shifting, right? Now, these entire things are the entire phenomena is what is called as resonance, right? And these structures are what are called as resonating structures. This NA is not there. Resonating structures or resonance structures. Okay, resonance structures or resonating structures. Okay, right. Now, can I represent all these structures in one picture? Right? I have 3 pictures now. I have 3 different structures now. All these things are different, right? Can I make sure that I can represent this entire 3 structures into one structure? Okay, now that structure is what is going to be called as a resonance hybrid. Okay, so from the name itself, you're able to understand a resonance hybrid is one which is going to be a combination of all the resonance structures put together. Okay, resonance hybrid is the resonance, I have so many number of resonance structures, all these structures put together as one, that is going to become the resonance hybrid. And how do we represent it? This is how we represent it in case of BF3. So let me not draw. So B, F, 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 normal. Okay, now there was a pi electron, right? There was a pi electron that was moving between among the fluorine atoms. Okay, now this dotted line, which I have drawn in red, means that the pi cloud is moving between this fluorine, and this fluorine. That is exactly what is happening, right? The pi bond was here. Now the pi bond was here. Now the pi bond was here, right? Now that this line, the dotted line which I have represented here, means what? It means that the pi electron which is there in the form of the pi bond and the lone pair is moving between these 3 fluorines. That is what you represent. Okay, maybe this is not clear that much. We'll see one more example. Okay, any questions till now? Anybody has? We will see more
Sir?
examples, more. Yeah, go on.
So why not put the dotted line from the bottom?
here also we have to keep actually. Here also we should do
So
3 times. Here, and here. All three should go. Okay?
okay, sir.
Right. Good. So now we will take a good example. This is just for you to understand what is back bonding, and from that we took resonance. Now that you understood how the pi electrons are going to move and stuff, right? Now we'll take a classical example. Okay. Before moving on to this, okay. Now I'm going to have BF bonds in this case, right? There are 3 BF bonds. Now my question is, all 3 BF bonds will have same bond length value, or will they have a different bond length value? Say for example, is this going to be a different value than this, and this is going to be a different value than that? Is it going to be like that?
Sir, after back bonding or before back bonding?
Anything in general. If that molecule is there, that means back bonding is already there. That is established, right?
Sure, then different.
Okay, we expect, right? Because one of the B is a double bond F, the other 2 are fluorines, normal single bonds, right? So obviously we expect this to be a shorter number, and these two bonds to be a bigger number. Okay, but don't you see, because of resonance, the double bond is getting displaced in between all the 3 fluorine atoms, right? Say in this case, this fluorine atom has double bond. Next case, this fluorine atom has. Sorry. And in this case, this fluorine atom has a double bond, right? So that means for all of the BF bonds, the bond length is decreased, and all the BF bonds will have same bond length. All the BF bonds will have same bond length. And why? What is the answer to this question? Why? The answer is, my beautiful friend, resonance. Okay, because of resonance, this double bond keeps shifting between all the 3 fluorine atoms. So all the 3 fluorine atoms have double bond character, right? It is somewhere between a double bond and a single bond, somewhere between a double bond and a single bond for all the 3 fluorine atoms. Okay, so for all of them, the bond length is decreased, and all the 3 BF bonds will have same bond length, because it is not only one fluorine, it is all the fluorine because of resonance that has a double bond character, BF double bond character. I hope you can make a note of the point. All BF bonds have same length. The why? Because of resonance. Okay, right, fine. So this we have established. Now let us take an example, another example. Let us take CO3 2-. That is what we're trying to start, right? Carbonate ion. Okay, fine. Now if I can just draw CO3 2-. Okay, right? This is the structure for CO3 2-. This carbon atom CO3 2-. I put 4 carbons. I'm simply wrong. C double bond O, O minus, O minus. All right. So this is sp2 hybridized carbon, trigonal planar. All these things we already know. All right. Now you see that I have a lone pair, right? I have a lone pair and I have a bond. Now please understand. 1 second. Just give me a moment. In the chat. Okay. Okay. So I have the CO3 2-. I told you that this carbon atom is sp2 hybridized. Now please understand. I have some kind of resonance happening here. Definitely the resonance is, the electrons are coming from oxygen because it is going to have a lone pair, and this carbon is going to accept electron. Okay, fine. Now the question is, if this carbon in this case is sp2 hybridized, what if it was sp3 hybridized? Will resonance happen is the question. Absolutely not. Can someone comment about this? If it is sp2 hybridized carbon, okay, resonance can happen. But if it is sp3 hybridized carbon, resonance cannot happen. Why?
So there
Can
is no
somebody
empty
comment?
orbital.
Exactly, right? In back bonding, you saw that the back bonding was able to happen, say some kind of resonance, like movement of pi electron, was able to happen because boron had an empty p orbital, or it had some space to accommodate more electrons, right? But if it was sp3 hybridized, all the three p orbitals, 1, 2, 3, all of them are involved in hybridization, right? But if it is going to be sp2, only 2 of them are involved. This would have been an empty orbital, right? So that is okay for me, right? So you have to check all this while you're writing resonance structures. Okay, when you write the resonance structure, you cannot just put it randomly. Be very careful. All right. Okay, so this carbon atom is sp2 hybridized, so no problem. It has an empty orbital, so electron can be accepted. Okay, right. Now let me make the pi electrons alone in different color. Okay, let me make this bond in blue color, and I'll draw the lone pairs also in different colors. Now O minus, that means 7 electron already had a bond, already 8 electrons are there. Okay, 8 electrons are there. 1, 2, 3, 4, 5, 6, 7, 8. Same way, 1, 2, 3, 4. No, 1 electron and correct. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this oxygen will have 2 lone pairs. Okay, right. So now what can happen is, now you see the negative charge can also is having a lone pair only. We will represent even negative charge in the form of a lone pair. Okay, right. So we understood that. I mean, we just represent the colors. Okay, of this O minus oxygen, O minus oxygen are 8 electrons, so 4 4 lone pairs, and this has 2 lone pairs. No issues. Okay, I think we should represent only 3 lone pairs, but doesn't matter. I have lone pairs. That's what it matters. Okay. Now what we have to understand is this carbon is having empty orbital, so it can accept an electron. It can accept 2 more electrons. Okay, now if I take up this 2 and make a bond here, see the arrow shooting from the lone pair towards the bond, I am going to make a bond. Okay, now if this happens, people, if this happens, okay, now obviously if this happens and I make a double bond, carbon would have had 5 bonds. Carbon would have had 5 bonds because already 4 bonds are there here, 1, 2, 3, 4. One more bond comes, obviously carbon cannot have 5 bonds. More than 8 electrons it cannot have. So what should happen? One of the bonds should break. Obviously, I cannot break a sigma bond. Sigma bond will not break. Only the pi bond can break. Okay. Now there is only one pi bond here, which is here. Now that pi bond will undergo heterolytic cleavage, and I'll show it like this. It will go towards the oxygen. Okay. Now, before I move on to write the resonance structure, we're going to write the resonance structure now. I have put the arrow marks. Right. Now, what you have to understand is, if this resonance was not happening, right? If this, whatever I'm telling you, if it's just like this. Okay. Now you would have expected 2 different bond lengths, 2 different CO bond lengths, one value and another value, one for C single bond O, another value for C double bond O. You would have expected, right? But no, you are going to get again only single value because I'm going to have resonance. We'll see this. Don't worry. Okay, so now I told you that this lone pair is going to come make a bond, and this pi one would have broken because carbon cannot have more than 8 electrons. Okay, so if I can read out the resonance structure, so you would have had C, O, 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 all single bonds, right? Now this oxygen would have had a negative charge, right? This pi bond is getting broken. So this oxygen would have had a negative charge. So more 3 unpaired electrons. That is 3 lone pairs. I shouldn't have 4 lone pairs, 3 lone pairs, right? And this oxygen has lost electrons, so the minus charge is gone. So I would have made a pi bond here, and I would have made only 2 lone pairs. This is remaining as such. 3, 4, 5, 6. No problem. Now see, the double bond is shifted between from this position to this position. Okay, from this position to this position. Okay, now again it can happen, right? Right? What can happen? Now you see that this electron can also involve, there's no partiality. All are oxygens, all are same lone pairs, there's no partiality, anything can involve, but accordingly the bond breaking should happen, right? Say now, this will make the bond, you can see from lone pair towards the bond, making the bond. Carbon cannot have more than 8 electrons, so this pi bond should break and go back to the oxygen. Okay, now another resonance structure. Right? Or how can I do this? C, all single bonds O, let me put. Okay, now the pi bond is where? The pi bond is here. So the pi bond is here, and the negative charge would have gone back here, right? And the negative charge is already here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now this would have had only 2 electrons. Okay, now the minus charge is gone. This oxygen got the minus charge. You can see this is getting the negative charge because that bond is getting broken and given to oxygen. Okay, all the 3 are, again it can go back. Now what can happen? Now this can come. These 2 electrons can come. These can break. It can continuously keep on happening. It can continuously keep on happening. If this happens, you will go back to the previous structure. Okay, if this, whatever the arrow shooting I show you, making a bond, double bond is here. Bond is broken, O minus is here, O minus is here, no issues. All right. Okay, so these 3 are the resonance structures possible. If you do one more time, you will go back to the first structure. Okay, you will go back to the first structure. All right. Okay, now these are all the resonance structures or resonating structures, however you want to call it. Right now, again, I will be able to represent them in one single structure. Okay, and that is what is called as my resonance hybrid. Okay, now I will draw the resonance hybrid like this. It is in red color. No, red I'll change. C O O O. Now the pi cloud is shifting. The red color pi, the blue color pi cloud is shifting between all the 3 oxygen atoms. Right. So I will draw something like this. Something like this, something like this. Okay, now this is my resonance hybrid. Okay, now what do I mean by these dotted lines? That means the double bond is shifting between this oxygen, and this oxygen. Okay, right? So that is what is represented by this resonance hybrid. You can see these are the resonance structures. Anybody has any questions? Anybody has any questions? Okay, I hope you understood that all the bond lengths, you expected that there is one double bond and 2 single bonds, but no, all the bonds are going to be between single bond and double bond, intermediate. Okay, so all the bond lengths would have been little decreased. That is, your single bond would have decreased, your double bond expected would have little increased because that can show single bond character also in one of the resonance structures. I hope everything is clear. All right, one more example. Now, I am going to give you ozone O3. Okay. Now, I want you to draw the resonance structures of O3 and send me in WhatsApp. Go for it. Okay. So, if you're wondering, and please put the charges very properly. Okay. So, ozone will have a structure like this. Okay. That is what is the structure of ozone O3. Okay. Now, again, you have lone pairs everywhere. Pi electrons can shift everything, you know. Make sure that you draw the resonance structures and you draw the resonance hybrid and send it to me in WhatsApp. Okay, I'll give you 5 minutes time. Go for it. 1 second, and I'll be back in another 1 minute. Yes, anybody's trying? Anybody got anything for resonance structures?
So how many resonance structures are there for O3?
2 or 3. How many you got?
Sir, I'm doing now. I'll just send you a pic.
Yeah. See, guys, it doesn't matter whether you think it is right or wrong. Whatever you got, please send me. I'll just know where you're doing it wrong. Doesn't matter whether it's correct or wrong. Please send me whatever you did. It doesn't matter. Obviously, at first time, you're not so like we are not Einstein to get everything right at first time. That's completely all right.
Sir, I have sent it to you.
Yeah, got it. Okay. I have put this electron here. Okay, your resonance structures are right, but the charges you have kept is little wrong. In the first structure, there is no negative charge, positive charge. Second structure
Okay, sir.
is almost right. The middle oxygen will not have any negative charge. Okay, almost right. You got it almost right. Good.
Okay,
Hamsini,
sir.
right?
Yeah, sir.
Okay, good, Hamsini. Okay, so going back to this, we will try to understand what is happening. Right? Anybody else wants to send me anything? Okay, fine. Now you see that there are lone pairs. Yes. Let me represent it with some other color so that it is visible. Okay, lone pair, lone pair, lone pair. 3 lone pairs. Okay, because it's a single bond oxygen. Okay, and this oxygen will have 2 lone pairs. And this oxygen doesn't matter because there is nothing is going to happen to this oxygen. Okay, now if I put I put the pi bond also in different colors. Okay, right. Now, if I put the electron here, 2 electrons donating to this, and obviously what should happen? This, I cannot have more than 3 bonds for this oxygen. So this bond should have broken to this oxygen. Okay, if I can maybe little more clarity. I will put the down bond and the up bond and then show this. Okay, I hope everybody gets this. This bond will come, make it, and the pi bond breaks. Now what should be the next structure? Oxygen, 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 single bonds. Okay. Now this oxygen has lost 2 electrons. I would say 1 electron in the form of a bond. So there'll be only 2 lone pairs. And this oxygen was neutral. Now, since it has lost electron, you have to give this a positive charge. Be very careful. Okay. And this oxygen, that is this oxygen, is nothing is happening to this oxygen. 1 bond broken, 1 bond made. 1 bond broken, 1 bond made. Nothing is happening for the middle oxygen. So no charge. Okay. But when I go to the last, this oxygen, right now it was neutral, now it is gaining electron, so I will put a negative charge on this oxygen. And how many lone pairs should I keep? 3 lone pairs I should keep, because already 2 lone pairs, 1 more is coming from the pi bond. And where should I put the pi bond? The pi bond is now here. Okay, now again this can go back. This can go back means what? This can come and this can go back. Again it will go back to the previous structure. That's it. Minus will be gone, plus will be gone, going back to the previous structure. Okay, so these 2 are the resonance structures. Right now, if I want to represent the resonance hybrid, can at least someone send me how the resonance hybrid will look? I think it's very easy, right? You just have to put a dotted line and send me. How does the resonance hybrid looks for ozone? After you send this, we will take a break. Okay.
Sir, I have sent you.
Yeah, correct. I'll 99% right. Just that it should be like this. Okay. So if I can make the oxygen, 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 the hot core, the pi electron is shifting from this oxygen to this oxygen. You should represent it in a single curve like this, Sridhar.
Okay, sir.
Okay.
Got it.
Right. Yeah, correct. Hamsini, you got it right. Okay, but make sure there's a connection in this place. There's a connection missing. Make sure there's a connection also.
Okay, sir.
Okay. Yeah. Other than that, absolutely fine. This is your resonance hybrid now. Okay. So again, you expect a double bond, single bond to have a different bond length, but both the OO bonds will have same bond length, little lesser than a single bond, but little more than a double bond will be the bond length here. Again, the answer why this is happening is because of resonance. And this structure, what you got here is my resonance hybrid. Okay. Fine, guys. We'll take a break. Time is now 12:37. We'll meet by 12:50. Okay. We'll meet by 12:50 and the class will go on till 1:40. Okay. Now you have 10 minutes break or almost 13 minutes break. Okay. So we'll come back at 12:50. The class will move on till 1:40. Right. You don't have to log out. You don't have to do anything. Just mute yourself, mute your videos, and then you can go. And we'll be back by 12:50. Okay. I'll see you soon. Okay. Hi guys. Are you guys back?
Yes, sir.
Okay. So I'll just wait for 1 more minute so that everybody comes back. 12:51. Start. Okay. So it is 12:51 already. I'll share my screen. Okay. Right. So we understood how to write resonance structures, what are the resonance hybrids. Now, till now, what are you seeing is only inorganic compounds. That is your ozone or BF3 or CO32 minus, CO32 minus, okay, organic. But still, most of them are mostly inorganic structures is what you saw. Okay. Now, if I can even have resonance structures in organic, that's why we're studying this in organic chemistry. Right. So let me take some examples. Okay. Say, I have CH2 double bond CHCl or C. Okay, I'll take the simplest of all molecule. Okay, I have a CH2 double bond CHCl. All right. Now this structure is going to have resonance. How exactly what it did in the previous case is very simple, right? I have 3 lone pairs on this chlorine. Okay. Now this carbon atom is sp2 hybridized, so still it can take up electrons. Okay, so now what will happen? This will come and this would have broken, because if this comes and makes a bond, this carbon cannot have 5 bonds. So one bond has to break, the next bond breaks. Okay, so if I can write the resonance structure, that would be CH2. Can I put CH2 minus, because the electron is getting donated to this particular carbon, minus. Now, this carbon, nothing is happening. 1 bond made, 1 bond broken. Nothing is happening to the middle carbon. So it will stay as such, CH. And you see, there is going to be a double bond between carbon and chlorine. Carbon and chlorine will have a double bond. And you see that the chlorine has lost electron. So chlorine will have a positive charge. Okay, I hope everybody gets this. What did I do here? Very, very simple, right? I donated electron, chlorine positive charge, double bond will come, 1 bond has to break, because carbon cannot have 5 bonds. So now it's gaining electrons. So this carbon will get a negative charge. Okay, I hope everybody gets this. All right. Now, for us to easily understand, okay, the resonance structures, the best classical example you can have in organic, or fine, we'll not go to the classic example right now. We'll take some other examples also. Okay, say if I have CH2 double bond CH, CH double bond CH, CH.
Sir,
Yeah,
sir, I have a doubt in the previous molecule.
yeah, tell me.
Sir, over here, as we know that chlorine is more electronegative, so it can try to pull the electron between the CH bond towards itself.
Yes.
So she
towards
will
this-
gain a
this
partial positive charge, and
Yeah,
hence
correct.
again, so due to the partial positive charge, the double bond between the C and C will again get broken.
No. So chlorine is more electronegative, so it will be able to pull electron towards itself. So this will have a partial negative, this will have a partial positive. Okay, go on.
Sir, so can that partial positive charge affect the double bond between the
Nothing
carbon
happening.
atom?
That's what. That is an entirely different effect. Here you're talking about inductive effect. Okay, yes, inductive effect is happening, definitely. Right? By inductive effect, this is actually going to be an electron withdrawing group. That means it is going to show minus I effect, because it is going to pull electron. But if I check resonance, right? Resonance, it is going to show me plus R effect. Again, in resonance, I have plus R and minus R. Don't worry about it. So that means in this case, chlorine is going to act as an electron donating group, because it is donating the lone pair to the carbon. Are you able to understand? Okay, both the things are happening. And which is more dominant? Resonance is more dominant. Inductive effect always has the least priority. Okay, inductive effect, hyperconjugation, the maximum priority goes to resonance. We'll see all that. Don't worry. We'll see slowly. We'll slowly introduce you to all of that. Okay, fine. So say next, if I have CHOH. Okay, now I have this structure with me. If I can write this little properly. Okay, now can you draw all the possible resonance structures for this molecule and send me in WhatsApp? Okay, you know where to start. You have to start with the lone pair and you have to keep on shifting the electron. Oopsie, 1 second, small change. Okay, now you do it. Do it slowly, people. Right? It's completely all right to take your own time. Okay. You have to put the charges very properly. Okay, that is one thing. Double bond properly, breaking properly, arrow marks very properly. Everything should be proper. I hope everybody is trying. Please do not sit idle, people. Please, this is not the time to sit idle. This is for you. This is the time for you to practice and make mistakes and learn how not to make the mistake. Mute. Okay. So Suprajit is correct. What you did is correct. Continue. There are more structures possible. There is your negative charge on carbon, that is 2 electrons. Shift. Continue. Till now what it is absolutely right. Okay. I'll give you 1 more minute, people, for you to send me your answers, and then I'll do this. Okay, fine. I'm going to do this for you, right? So you understand that this oxygen has 2 lone pairs. Okay, the first step would be to make a bond. Okay, the first step would be to make a bond here, right? Obviously, this carbon cannot have 5 bonds, so this bond will break. No problem. Okay, now I can rewrite this structure as CH2 double bond CH. Now this carbon is gaining electron, negative charge, 2 electrons are there. Okay, with CH double bond oxygen having a positive charge, because the lone pair is coming, oxygen is losing electrons, so a double bond OH plus oxygen having positive charge. Okay, people, still you can continue, right? Now you see that this is a lone pair in the form of a negative charge. This can come here and this can break. Again, if this comes, make a double bond, this carbon cannot have 5 bonds, so the other bond will break. So the next structure, I can write it as CH2 minus, because the lone pair, I have 2 electrons coming as lone pair, means the negative charge, 1 bond, CH double bond. Now there's a double bond between these 2 carbons, right? Because the lone pair is coming, and the other lone pair still exists. CH double bond OH plus minus. Okay, right? So all these 3 are the resonance structures. Okay, now we don't have to go into the resonance hybrid. It will be a little complicated. All you have to understand is this is how you do the arrow shootings. This is how you show the positive charge, negative charge, positive charge, negative charge. All these things are very, very, very important. All right. So one more example. Okay, first you copy this down. Then we'll go to the next example. Okay, right. I hope you have copied. Right. Next example, let me give is, see, you could have actually understood 2 things from the previous example. One thing from the previous 2 examples. What resonance can happen, right? Resonance can happen if I have alternate pi electrons. What do you mean by alternate pi electron? You see, In this case, the first case, 1 pi electron, no pi electron, pi electron. Isn't it? Pi electron in the form of a lone pair, nothing in this. But next has, I have a pi bond, again a pi electron. Right? Pi electron, no pi electron, pi electron. Correct? Here also you see pi electron, no pi electron, pi electron, no pi electron, pi electron. Alternatively, 3 times it is happening. That is why you're able to continue also. Right? But for example, if I would have given you something like this. Okay. Now, do you think any resonance structures is possible here for this particular molecule? Yes or no?
Sir, only one.
Where one? Nothing. No resonance structures are possible. Where will you start from?
Okay, no, sir, never mind. No, it's not possible.
Nothing, right? So I have a lone pair here. First of all, this lone pair cannot even come here. This is not possible because this is sp3 hybridized. Like this cannot. There is no place for the electron to come and sit here. I mean, come and sit here. So this is sp3 hybridized. Nothing will happen. But again, here also nothing will happen. You can even maybe show it like this. Maybe you can break this bond and show it like this: CH2 plus, CH minus, CH2, CH2, OH. But really doesn't make any sense. Again, I know that I have a negative charge here that will come back to give me the structure. Maybe that's all you can do. Right? So I need to have alternate pi electron, no pi electron, pi electron, pi electron, no pi electron, pi electron. Okay, alternatively it should be present. Only then resonance is possible. Okay, right. Now there is a small thing that I want you to know. There is something called as conjugation. Okay, sometimes they use conjugation and resonance very similarly. They are used for similar words. I mean, say in similar situations, but there are certain differences. Okay, now whenever you have only pi bonds present and if resonance happens, okay, if you see that there are only pi bonds, I'm not talking about pi electrons, I'm talking only about pi bonds. In a compound, there is only pi bond. And if resonance structures you write, this resonance is what is called as conjugation. Okay, now let me give you an example. For example, look at this. If you had CH2, okay, now I have this molecule, right? Now, okay. Okay, now you see pi electron, no pi electron, pi electron. Criteria satisfied. Okay, pi electron, no pi electron, pi electron. Alternate pi electrons are present, so resonance is possible. But this time I am not going to call it as resonance. I am going to call it as conjugation. Okay, I'm going to call this as conjugation because I see only pi bonds. There are no lone pairs, no negative charges. Right, only pi bonds I'm seeing, and those are also involved in resonance. But that we will not call it. We can call it as resonance, obviously, but say more specifically, right? Special case, right? So we'll specifically call it as conjugation. All right. Now I can show it like this. How can I show? Let me read out the structure for you again because it will become a little clumsy. CH2 double bond CH double bond CH2. Okay, now say first bond I will go for heterolytic cleavage. Okay, let me make it like this. Now if you put the arrow mark towards this carbon, nothing will happen. Okay, that is it. That's it. You cannot do anything else. You can check if you want, but I'm putting it towards this carbon. Okay, so the resonance structure I can write like this: CH2 double bond CH. This carbon is gaining electron, negative charge. And this carbon is losing electron. A double bond is gone, only a single bond. So CH2 plus. I hope everybody gets this. Very easy. Carbon losing electron, positive charge. Carbon gaining electron, negative charge. Okay, now what can happen? Now you see again I have 2 electrons here in the form of a negative charge. this can come here, and obviously this carbon cannot have 5 bonds, so this bond will break. This is proper resonance. Okay, this what we are writing here is proper resonance. But how we started this? We started with the help of a conjugation. Okay, conjugation. What do you mean by a conjugated double bond? Means alternate double bonds are there. Double bond, single bond, double bond, double bond, single bond, double bond. Right? Those kind of species are what are called as conjugated species. Okay, now we start with conjugation because there are no pi electrons. I mean, there are no other type of pi electron, only pi bonds are there. So we call it conjugation, but this we can perfectly call this as resonance. Because what? Because starting with a negative charge, lone pair. Right? So now that will come here. Now, how can I write this? Now this will become CH2 minus, right? Because this carbon is gaining electron. This carbon, nothing is happening. One bond made, one bond broken. Nothing happened to the middle carbon. But that is going to have a double bond with this carbon. And this is going to have a positive charge. That's it. Right? Again, we can, yeah, go on.
Sir, what if there was a C double bond C in the middle and then CH3 at the ends?
Wait, let me draw structural. Okay, so you're telling CH2 double bond, CH
No, sir.
double bond. Okay.
No, sir.
Wait,
CH3 single bond,
wait,
CH double bond CH.
Wait. CH3.
Single bond CH.
Okay.
And then double bond CH.
Okay.
And then single bond CH3.
This one, no, this cannot have resonance. Why? Because I have pi electron, no pi electron. Next case, I should have a pi electron. Alternate pi electron should be there. For something to be alternate, I require at least 2. I have only 1 here. Okay. First of all, say if you say you break this, okay, you break this heterolytically. Okay, you break this heterolytically and show me that it is going to be, sir, positive charge. This is going to be negative charge, single bond only, and say there is a CH3. Okay, but can you shift it to this carbon? The answer is no. Why you cannot shift? Why can't you shift?
Sure, because it's already full. I mean,
exactly. This is sp3 hybridized. This is sp3 hybridized, no empty orbital, so it cannot transfer like this. So resonance is not possible here. Okay. Right? I need to have alternate pi bonds, alternate pi electrons should be there. Okay. So now these 3 are going to become your resonance structures. Now what I want you to do is I want you to go back from this to this. Show me the steps. I want you to start from this and I want you to end with this first compound. Go back. Do the exact reverse. Do the arrow marks reverse. Show me the charges. Show me the shifting of bonds and put it in WhatsApp for me. Go for it, people. I give you a very easy task, but do it properly. No mistake should be there. So you see that there are 2 electrons here. Negative charge means 2 electrons.
Sir, I've sent you.
Okay. Okay. Plus, minus. Yes, correct. Absolutely. So Prajit got it right. Anybody else want to send me? I'll give you 1 more minute. Okay, fine. I think nobody else is sending. Let me clear this for you. Okay, so in this case, we are going to start with this 2 electrons donated to the next carbon. So obviously this carbon cannot have 5 bonds, so this bond will break. Okay, so if I can rewrite the structure, CH2, now it had a negative charge, that negative charge is gone because it's donating electron, right? So now I have a double bond. Okay, again, for this carbon, nothing is happening. 1 bond made, 1 bond broken. So CH, again, nothing, right? To this carbon, there was no electron, there was no charge. Now the pi bond is broken, given to this. So this carbon will have a negative charge, CH minus. Again, the other carbon remains as such, CH2 plus. Okay, and that's it. I have a lone pair. This will come here. Negative charge gone, positive charge gone, because this is donating electron, this is accepting electron. So this, you will go back to the previous structure, the first whatever you started with. Okay, right? So this is how you draw your resonance structures. More examples coming, more examples coming. Okay, say if I give you fine. Let us start with something simple. Okay, so can you do this? Resonance structures, send me in WhatsApp. I want everybody to participate. Okay, the more you participate, the more you'll make mistakes, the more you will learn. If you are not going to do that, I'm so sorry. Well, if you're going to do this now, welcome to the heaven of 12th. If you are not going to do this now, welcome to the hell of 12th. Ask your seniors, okay? Ask your seniors, how important is this? This particular chapter is very important. Very, very. That's why we're taking it very slow also. I'm going from the scratch, taking little by little to the next higher levels. Hope you get benefited out of this, obviously only if you're interested. If not, I'm so sorry again.
Sir.
Yeah.
Sir, but how does this structure have alternate pi bonds?
I didn't need to have alternate pi bonds. I need to have alternate pi electrons. That's all I need. Alternate pi bonds for conjugation. Alternate pi electrons if I have. I am so sorry. You are absolutely right. I am only having that. I am the culprit. The pi bond should come here.
Okay, sir.
Yeah, correct. Thank you for this. Yes, this is the correct structure, people. Please change it. This is not a that tough of structure, I guess. I didn't get any response yet. Okay, so I think it's very simple, guys. So nothing here. We are doing it for straight chain here. It's only a ring structure. That's it, right? So I know I have 3 lone pairs on this oxygen, right? Say one lone pair can come here, make a bond, because this carbon atom is sp2 hybridized. Obviously, this carbon cannot have 5 bonds, so this bond will be broken, given to the next carbon atom. That's it. All these are carbons, right? So I will be able to represent this as double bond O, right? Again, if I show you properly, O minus, I'm telling there is a lone pair which will come here and this bond will break. Okay, so now I made a double bond. The oxygen's negative charge is gone because it's donating electron, and this carbon is gaining electron. So I would have had a negative charge here. That's it. These two are the resonance structures. Very simple. I hope
So
everybody
can't
gets
this be further resonated? Like,
yeah, it can be further resonated like this, and you can go back to this to get back the structure.
only 2 structures will be there, correct?
Yes, only 2 structures. That's it.
So can I
Right. So if
send
you
you
ask
my
me, can I?
structure?
Yeah, please. Go on.
But then mine is the first 2 structures are correct for mine, but then I don't know
Okay.
how to go about afterwards.
Go for it. Just send me the 6 structures. I'll tell you what
Yeah,
went wrong.
okay. So I have sent it.
Kana, you are shifting this pi bond to this carbon, right? Basically, this carbon you are shifting. What is the hybridization of this carbon? This carbon, what is the hybridization? Is there any pi bonds on this carbon? This carbon, basically.
No.
So what is the hybridization here? sp3. Now you have to understand that there are already 2 hydrogens here. Okay, 1, 2, 3, 4. 4 bonding atoms, steric number 4, sp3 hybridized.
Oh, okay, sir. Okay.
Understood? So you cannot
Yeah.
shift it. There are no empty orbitals here, so you cannot shift. That's it. These two are the only structures possible.
Okay, sir. Got it.
Okay, good, good. Right. See, guys, like this 1,000 questions will come in resonance. I know. First time you're doing this, I know you will get so many questions, but I think most of you are not trying. That's why you're not. That's why you're not getting questions. But afterwards, if you suffer, do not blame me. Okay. Right. Good. Fine. Moving on. Moving on. Now let me increase the pace. Okay. Say I have this. Okay. Now I have 2 pi bonds and this electron. Go on. Make the resonance structures. Or I have this one. Okay. Now I want you to go to this one. I want you to end the resonance structure with this one. See how the pi bonds have shifted. Okay. Here I have here, and here. You see where are double bonds? Here, here, and here. I wanted to start with this and end with this. Tell me all the structures. Slowly you do, right? Be careful.
Sir, could you show where it should end? Okay.
Sir, I've got it, sir. I've sent it to you.
Yeah, 1 second, Hansen. Okay. 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 Good, Hamsin. Very good. Very good. You got everything right. Amazing. Amazing.
Okay, sir.
Right.
Sir, even I've sent it.
Yeah. Seeing.
Sir, I also sent it.
Yeah, I saw. Coming. So this is okay. Yeah. So Brigitte, yours is right. Everything is fine. Good. Coming to Sri Giridas. Okay. 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 Absolutely. Yes, Giridhar, yours is also absolutely fine. Very good. Right. I hope everybody is able to get the hack. I don't know about others because you're not sending me. Okay. If you send me, I will know whether you're right or wrong. I can correct you. Okay. This is where you're doing it wrong, but nobody else is sending. So I'm going to give the answer. Okay. Now let me start with this. Okay. I have a no minus, double bond, double bond, double bond. Now this is nothing. This is what is called as a phenoxide ion. We don't have to go to the details. It's giving you an extra information. Okay. So here you have electrons to start with. So you will come, you will break this. This is the first step. Okay. Double bond O will come. Now the negative charge on oxygen is gone because it's donated electron, right? And this pi bond is broken and given to this negative charge. The other things remain as such. Okay, now here I have 2 electrons. This will come, make a bond. Obviously, this carbon cannot have 5 bonds, so this will break. Next structure, right? Double bond O. I have made a bond here now because the bond is here. Now this bond is broken, right? So you will form a negative charge. The other thing remains same. Next step, this will come, this will break. Double bond O, a bond here. Now you would have made a bond here and this bond is broken. So a negative charge here. Now the last step, this bond will come and this bond will break. That's it. This carbon cannot have 5 bonds. So it will break to give the last structure which I wanted you to give. O minus will come back. You would have made a double bond here, already a double bond here and a double bond here. Absolutely. All three of you got this. Very good. Got this. Very good. Right. I don't know really about others. If you have any doubts, please ask me, at least personally. You can WhatsApp me. So this I'm not getting, that I'm not getting. Please ask me. I'll be able to help you out. Okay. So people, I think we'll finish with stop with this for today. Okay. We'll continue with the next class. We'll continue with resonance and other aspects of resonance. Now you understood how to write the resonance structures. Okay. Now because of resonance, I told you one consequence was double bond. Even though we expect the bond lengths to be different, but I'm going to say that the bond lengths are going to be same for so many molecules we saw, right? And next, what I want to understand is how resonance brings in stability, okay? And how resonance plays a role in deciding what kind of product you will get, especially in these kind of structures, okay? When you go to the different types of reactions, again, you'll study this. Very, very important, okay? So we will see all that in the next class, okay? If you don't have any questions, we can wind this up. Any questions, anybody?
Sir, in the resonating structures, the first structure and the last structure should be the same or not? Like not necessarily.
Not necessarily, in the sense that if you start writing the structures, eventually whatever structure at last you end up with, you can go back to the previous structure. We saw so many examples like that. Okay, yeah. But it is not necessary to show it every time. Not necessary. Okay. It is understood, right? But okay. If I ask you, like I asked you, now you start with this, you end with that. Like that, if they ask you, definitely you should show everything. You should show. But if they don't ask you, whichever is the last you got, you stop it there. It is by default understood that way. You can even go back to the first structure. Yes.
Okay, sir.
Okay. Right. Any other questions anybody has? Okay. Thank you so much, people. We'll meet again next week.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah.